the ultimate techniques either, but it's already a generalization compared to data flow analysis. So you can actually combine the techniques, and you can have, say, a sensor that is one of data flow analysis, and from that you have a top-level tool that does model checking, so construct the automata, and say the automata can hold constraints on the variable, say, this variable is between such and such value, and in this other state, we have this variable assignment, and so we change the constraint, etc. So you can combine multiple techniques. Those techniques are not like exclusive. You can combine the techniques. Any question about that? Is it clear? It's okay, Hitesh. I mean, I'm here to answer questions, so if you have any question, if you don't understand, if I'm not clear, just let me know.
You went through the static analysis way.
Yes, so everything of this is static, so we never need any code execution. We never need to execute the program. It's all done from the source code, actually. You have also techniques to do that on binary code, but what we have done is on source code because we have the source code, so we don't bother doing any kind of reverse engineering. Yeah. I'm going to mention this later. So actually we have two modes. One is purely intra-procedural, and the other is inter-procedural. And so one is just working inside a function, like in each function independently, and the other is actually propagating a result from function to function, and I'm going to tell the difference a bit later. As I said, for a million line of code, we have around 100 warnings for about 3,000 allocation types. So it filters out 99% of the allocation types. And on those, we have around 10% that are real bugs. So basically, well, do the count. Yes, it's defined, the malloc zero, again, the malloc is 0 is defined in the standard of C. So it's allowed, like for example, you can have malloc 0, realloc. So you can malloc 0 and then realloc memory like that, and it's perfectly valid. That's right, because you could just do a macro that says, okay, I'm going to check the size of malloc, and if it's 0, then I filter it, and the thing is, you have legitimate uses of malloc 0, so you just cannot do that in the general case.
Really intuition as to when the state space or what's floating around the table around it based on the type of code you're looking at and the structure?
Generally, you have state explosion when loops. As soon as you have loops, of course you have abstraction technique that allows you to reduce state space for loops and everything. But what we have, well, as soon as the loops you're analyzing don't change the valuation of the property you analyze, the formula you analyze, then you don't care how many loops are there. There are, because if the loops don't change anything in the property you're analyzing, then you don't care how many loops are there. So, well, if you have like nested loops and things like that, then you're going to have a state explosion pretty quickly. Okay. Anything else before I continue? There is a public version of the tool, but it saves pretty poorly. So we have like the public version. It scales to around 30,000 lines of code, which is very few, obviously. So you can analyze the driver with it. and it plugs into the Microsoft compiler, so it's going to work as soon as you can compile the code you want to analyze with the Microsoft compiler. For example, I'm not sure you can analyze the Linux kernel with this, because I'm not sure if you can compile the Linux kernel with the Microsoft compiler. But the techniques are generic. I mean, like, you can apply those things to other framework, with other frameworks, and the techniques are pretty, very well documented. Third technique, which is actually the technique we use, is called theorem proving. So it has a very alien name, so don't be afraid of it. Theorem proving, the theory of theorem proving is really old. Like the foundation of computation, basically, when you try to prove that the code is doing what it's supposed to do. So basically, as I say in the slide, theorem proving is a mathematical technique where you try to establish functional verification of code. So at each step of the code, you're going to infer a logical formula that holds as this program plays. So you start by empty formula as the initial condition of the program, and step by step, you're going to construct the formula that holds as the program point. So these formulas that we infer from state to state is called the verification condition of the C. And then we have basically at every program point that we're interested in analyzing, for in our example, like all allocation types, we put assert, say assert size different than 0. So